Hello everybody, this is Mrs. Lindsay. Today we are starting our first day in the probability unit. This is actually from sections 11.1 to 11.2 and the MHH portion of our textbook. Okay, so of course we start off the unit here. We're starting with some basic definitions. In the study of probability, you're interested in quantifying the likelihood that various outcomes will occur in some random process. Much of probability in the very beginning was dealing only with gambling and different types of games. However, then it was started to be applied to the sciences in the 18th century and the 20th century. Then it was really developed by, I'm going to mispronounce these names, but I'll just let you read them, by these three mathematicians. Okay. So an experiment is some process in which individual outcomes are unknown, but in which long-term patterns are predictable. Okay, so we do assume that experiments can be replicated. Okay, that is, they can be replicated under the same conditions as many times as we desire. The set of all possible outcomes in an experiment is called a sample space. An event is a subset of the sample space. That is, an event is a collection of one or more outcomes. There are only two ways to find the probability of event E. Okay, so a couple things I want to throw out there to you. When we're referring to this, we're referring to something very similar to, like, if I flip a coin, I get heads or tails. The probability of that occurring of getting a heads is a half, probability of occurring tails is a half. However, if I'm talking about a lotto ticket, the probability is not a half, even though there's a winning ticket and a losing ticket. So again, we're really referring to more of the heads and tails type situation there. Theoretical probability is we assume that the sample space consists of equally likely outcomes. Okay, so our sample space consists of equally likely outcomes. The probability of this event, probability of event E, is the number of outcomes in E over the total outcomes in the sample space. And you'll hear me kind of say this in the numerator. I'll refer to this as like the winners. This is what we're looking for, right? Over the total amount of outcomes. So let's just start with one example here. Okay, so we have a bunch of marbles. It's drawn at random from a bowl containing 3 yellow, 4 white, and 6 blue. We want to find two things. What's the probability that a yellow marble is drawn? And then we also want to find the probability that either a yellow marble or a blue marble is drawn. Okay, so if we're first drawing a yellow one. Right, well, we know we have so many yellow, so many blue, etc. So let me just go ahead and write that down here. We have 3 yellow, 4 white, and 8 blue. Well, if I add those all up, that's going to give me a total of 15 marbles. So that's where my denominator is coming from. But in this case here, we want to know how many yellows. Well, there's a total of 3, so the winners, 3 over 15. Or 0.2. Now, I do not care how you write your actual answer for probability. It can be written as a fraction, a decimal, or I can even convert that to 20%. Either way is fine. I'm okay with all 3 of those. Obviously, if the book specifies one way or other in the directions, just follow the directions. But again, either way is fine. So let's now take a look at B. Now, B said either yellow or blue. So either yellow or blue. Okay, so we have 3 yellow, 8 blue, a total of 15. So 8 plus 3 gives us 11 out of a total of 15. So that is our probability of getting either a yellow or blue. Second example. There are 2,598,960 possible hands in poker. If there are 36 possible ways to have a straight flush, Find the probability of being dealt a straight flush. Well, again, number of winners in this case is 36 of them out of the total number of 2.59896 million. And again, I'll take that as a decimal or a fraction. Either way is fine. This percent is rather low, which again, I would take that as well, but either way, that would be fine. So again, some definitions. Empirical probability. If the event is repeated n times, then the probability of the event E is, again, the number of times that E occurs over the number of times the experiment is performed. So here we have a cup is flipped 100 times. It lands on its side 84, bottom 6, and top 10. Find the probability that it is on the top. So again, and the numerators are winners, so to speak. So we're looking for how many is that? Well, that's 10 out of the total possibility, which in our case here is out of 100, so 10 out of 100, so 1/10, or again, if you'd like to put that as a percent or decimal, you're welcome to do so. Another example. The school has 820 male students and 835 female students. If a student from the school is selected at random, what is the probability that the student would be female? Okay, try this one. Push play when you're done, and then we can go over the answer and check it. All right, so hopefully you saw we're looking to see total number of female students over the total number of students. In this case, we actually had to add these. So your fraction might have originally been 835 over 1,655. But either way, you get it 50.5%. Again, I don't mind if you write it that way, approximately, because we are rounding, or 0.505. Another example. A survey was taken to gauge the level of product recognition in the urban area. Of those surveyed, 830 people recognized the symbol for Nike, while 184 did not. If a person is randomly chosen from the survey, what's the probability that he or she will not recognize the Nike symbol? Again, I would like you to go ahead and pause this one, push play when you're ready to check your answer. Okay, not recognize. So that is the 184 over the total number. So in this case, we have, adding those together, 1,014. 184 over 1,014 gives us that probably a 0.181. Okay. All right, so law of large numbers. Both methods of computing probabilities give the same results, provided n is very large. That is, in a very large number of trials, we expect the proportion of occurrences of E to approach the probability of E. So again, very large numbers, super important there. This basic fact is used by marketers and social scientists to compute probabilities using survey data. Okay, so again, really large numbers. So here we have a nice table. In this table it says a university cafeteria surveyed the students for their coffee preferences. The findings are summarized as follows. Okay, so again, female, male, who drinks coffee, who prefers regular coffee, who prefers decaf, and then all of our totals either at the bottom of the columns or over to the right hand side of the rows. So let's just talk about part A here. Okay, so on A it says does not drink coffee. Okay, well, all of these people do not drink coffee, so that's 41 out of our total number. So 41 out of 497 is going to be our probability when they don't drink coffee. Okay. What about B? What is the probability, select a random, that they're male? So in this case, the total number of males is 26. Oh, actually, I think that is wrong. Because right here, that's 18. Yeah, those should be 260. If I added that up, yep, that looks right. So it should be 260 out of 497. That was just a typo. I'm not going to have you actually validate the numbers in there. That's just a typo. 260 out of 497. Okay. And let's do female who prefers regular coffee. So who prefers is in this column, but female is here. So we're looking here at 145. So 145 out of our total number of 497. Okay. Next example. Of 400 college students, 120 are enrolled in math, 220 are enrolled in English, 55 are enrolled in both. Again, find the probability that a student is enrolled in math. So in this case, we have math. We clearly see that that's 120. Now we need to actually figure out what's the total number. Okay, so it says the student is enrolled in math. We have 120 in math, 220, 55 enrolled. We don't just add those up. It actually tells us how many we have right here. So we have 120 out of 400. Now again, you can divide that, you can reduce that, you can write it as a percent. I'm fine with any of those. Okay. Student is enrolled in English. Well, 220. Again, out of our 400. Student is enrolled in both. Again, they give us that number as well. So far, not too bad. Okay, so now let's talk about D. The student is enrolled in either math or English. Well, how do we calculate this? So hopefully you're thinking about, yeah, I know the probability of how many are in math. And I also know the probability of how many are English. But some of those overlap. All right? Sorry, my stylus is writing a little awkwardly there. So we have to subtract the probability that they're in both. Again, we can't repeat them. So the probability in our math, we did that up here, 120 over 400, plus the probability they're in English, 220 over 400, minus the probability they're in both, 55 over 400. So they all have the same denominator. Add those guys all up and subtract 55. You should get 285 over 400. And that's for D. What about E? The student is enrolled in neither math or English. Well, sometimes it's easier to find when they are enrolled. So we actually just did that in D. We found when our students enrolled in either math or English. Now we want to find out when it's neither. So if I literally just take, so E is going to be over here, 1 minus the probability of what we just did in D. So you'll see it written like this. Either math or English. So if I do the opposite of what I just did right here, so 1 minus 285, run out of some space here, over 400. I'm going to have to continue this up here. Sorry about that. Let me go up here. So I can just erase this guy right here because that's causing me some fits. So 1 minus 285 over 400. And again, 400 over 400, you can just use your calculator. 115 out of 400. And this is for E. Sometimes, again, it's easier to figure out when does this occur and subtract it from 1. Because everything should add up to 1, or in other words, 100% with these. And we'll actually talk about these two scenarios, D and E, as we continue along with the notes here. But there are some basic rules of probability. Number 1, The probability of an event E is the sum of the probabilities of the individual outcomes in E. Okay, in particular, if the outcomes are equally likely, then we get this definition of theoretical probability. So again, the winners over the total outcomes. 2. Probability of any event is between 0 and 1. Again, because this is 0%, 0% to 100%. Remember, you can write it as a percent, you can write it as a decimal, you can write it as a fraction, so these are decimal versions here between 0 and 1. Okay. There are 3 ways to write a probability, which you've also talked about: a fraction, a decimal, a percent, and I don't care which way you would like to write those. Interesting that that just did that. Okay. Number 3. The sum of the probabilities of all possible outcomes is 1. Very similar to what we were just talking about with our last example there. So the probability that they were either math or English versus the probability that they were neither in math or English, we could just really subtract them because they both added up to 1. Okay, so if we think of the sample space S in a given event, the probability S is 1. At the other extreme, the null set or the empty set, a lot of times you'll see it just written like that, is also an event. The probability of this occurring is 0. And we'll actually run through some examples of those as well. 4. The probability that an event E does not occur, so again, this is just like what we were talking about there, is 1 minus the probability E does occur. Okay? And the last one. If 2 events, A and B, do not have any outcomes in common, super important, do not have any outcomes in common, then the probability that one of the other outcomes is the sum of the individual probabilities. So it says if events A and B are disjoint, it is simply the probability of A plus the probability of B. So this is like the marble problem. What was the probability? It was yellow or blue. We literally could just add both of those because there was no marbles in the bag that were a mixture of the 2 colors. However, when we were talking about being enrolled in a math or English course, there were students who were in both courses, so that it would not be this exact same thing because they were in common classes there. Okay? So we'll talk about how we adjust that, and basically you just subtract off the probability they're in both. Counting method of probability can be used only when all outcomes in the sample space are equally likely to occur. Luckily, the sample space can always be determined in such a manner. Okay, so let's talk about another example. A coin is tossed 4 times in succession. Find the probability of getting exactly 3 heads. B. Find the probability of getting at least 3 heads. Okay, so let's deal with the first one. Exactly. Well, to describe an outcome, the result of 4 successive tosses, we need to actually kind of record what's going on here. Now, some people might think this takes a little while to do, but we actually just need to write down all the scenarios. So if I got a head the first time, I could get this scenario once, and then I could get it where I got a tails. So I'm using H for heads, T for tails. So, and then I keep going. I need to write all this list out. But if you go in order, and I went ahead and wrote these down. So here we have all heads. Then I just started putting in 1 tail. And I put it in, again, different spots here. So kind of highlighting where those are. Let me switch colors here. But this is the different occurrences. So now I put in, and this second one, I put in 2 tails. And again, switched where they could occur. And the 4th column, I put in 3 tails. And I switched where they could occur. And the last one, I put in all tails. There are 16 total situations where this is happening. So if we're trying to find the probability of getting exactly 3 heads, okay, so where does that occur? That is happening here, right, where we have 3 of them. So we have 4 of them out of a total of 16, so 25% or 0.25. Again, I would take this as an answer. I would take 1/4 as an answer. I would take 25% as an answer. All of those would be fine. So now B does change things just a little bit because now it says at least 3. So not only do I include where there's 3, but I also include where there's 4. So that adds, if I go back to my chart here, that adds one more where there are 4, what was it, heads. Yes, so now that also adds that one in there as well. So now I have a total of 5 out of 16, so 0.3125 as my probability. Okay. Genetics. There's also some probability here. Okay, so we talked about the randomness of the study of genetics. To study the flower color of certain pea plants, he found that pure red crossed with pure white produces red. So he's, in other words, theorized that red is dominant. So capital R is standing for your red is dominant. White is recessive. That is designated by the lowercase r. The pure red parent carried only genes for red, and the pure white parent carried only genes for white. Again, lowercase r. So you have all these different ideas here. So if I have my first parent and the second parent. So if the first parent is, again, carrier of red, the capital R's, second parent is carrier of the white, here's your scenarios. Okay? All of these, again, would lean to red because red is dominant over the white. And since they all have a red, these would all be red. But now if I do a red and a white, with the second parent also being a red and white, now I do have a situation where I have 2 whites together. Okay? So let's look at these probabilities using these tables here to answer the next example. So referring to the second and third generation, so again, we're referring to this chart right here. Determine the probability that a third generation will be red, and then the second one we want to determine when it's white. Okay, so again, red. Where are they red? That is where you see a capital R anywhere. So that occurs. So what I have circled here are my outcomes. Where I see a capital R, it would be red. And notice that occurs in 3 of them. So it'd be 3 out of 4. Okay. So this is again where it's red. Part B says, okay, when is it going to be white? And again, we have 2 lowercase r's. That's the only case it'd be white, so it'd be 1 out of 4. Okay. All right, what about rolling some die here? When the single fair die is rolled, find the probability that each of these events occurs. Okay. First one, probability 3 is rolled. B, a number other than 3 is rolled. C, number 7 is rolled. And D, number less than 7 is rolled. Okay, so we have 6 possible outcomes from rolling a die. 1, 2, 3, 4, and 5. So the first scenario says, okay, what's the probability of rolling a 3? Well, there's 1 out of a total of 6, so 1, 6. Well, if it's not a 3, we have 1, 2, 4, 5, and 6. 1, 2, 4, and 5, and 6. So that would give us 5 out of 6. And again, notice this is equivalent to 1 minus the probability that it's 3. We could have done 1 minus a 6th. Gets us the exact same answer. Now, 7. Probability of rolling a 7. There is no 7, so that's why it's 0. So again, this is the exact same idea here. If it's less than 7, all of them occur. So that's why it's 1. Okay? So again, this kind of shows the negation of what you're looking for. They always have to add up to 1. So 1, 6, and 5, 6 added up to 1. Okay? That's one of our properties there. So leading to that a little bit more, the probability of an event not happening involves the complement and subtraction. More specifically, the probability that an event E will not occur is equal to 1 minus the probability that it will occur. Okay, you call that the complement of E, or you might hear me also say E prime. Either way is fine. So if E is an event, then the complement of E consists of all the outcomes that are not in E. So the probability of the complement, both of them added together should add up to 1, or the probability of the complement is 1 minus the probability the event actually does occur. So let's try an example here. When a single card is drawn from a standard 52 card deck, what is the probability that it will not be an ace? Well, it might be actually easier to figure out what's the probability it's an ace. Okay, so hopefully you know your standard deck of cards. If you do not know what's in your standard deck of cards, there's 4 suits, 2 are red, 2 are black. Please take a little bit of time. Maybe just go online, research that, make sure you know what's in the deck of cards, because I will make that assumption that you know that. If you have trouble about that, please let me know. Okay, but take a moment and look that up if you don't. So it's definitely a little easier to figure out, hey, what's the probability it's an ace, because there's 4 of them. So 1 minus 4 out of 52. So that gives us 48 out of 52, or 12 out of 13. All right, going back to the word or here. Compound events involving or. If we want to know the probability that A or B occurs, then we should look at all outcomes that are either in A or in B, or possibly in both. Okay, so we definitely are going to involve addition with this, and occasionally subtraction. If they have no common outcomes, they're considered mutually exclusive, and we literally just have to find the probability of each of them occurring and add them together. Again, that is if nothing is in common. So, for example, like the marbles, there were no mix of yellow and blue marbles. Okay, so here, let's look at this example. If a single die is rolled, what is the probability of rolling either a 2 or an odd number? A 2 is not an odd number, so we do not have to worry about the overlap of that. So we can just, they're again mutually exclusive. We can find the probability of 2 plus the probability that it's odd and add those together. That would give us it's a probability of either rolling a 2 or an odd number. But what if it said what's the probability of rolling a 2 or an even number? So if I just changed one word, now these events are not mutually exclusive. So again, what would we do? Well, we'd still add the probability of the first, probability of the second, but then we again subtract where they both occur. Okay? Otherwise, we're going to have repeats. You would just count things twice in some cases. Okay, so again, double counting is what we're trying to get rid of. So here's an example of that. When a single card is drawn from a standard 52 deck of cards, what's the probability it will be a king or a diamond? And again, if you're not up on what your cards are, every suit has a king. So there is a king that is a diamond. So we would be counting that card twice if we did not subtract off the fact that we had a king being a diamond. So it's both scenarios. So again, 4 kings, 13 diamonds. One of those diamonds is a king, so we have to subtract that off, otherwise we counted it twice. Okay. So again, just kind of summarizing that here. Exclusive, mutually exclusive versus not. And it's okay to actually always do the first one, because this could just be 0, which would and just give you the bottom if they're mutually exclusive. But it's a good idea to think through those as well. Okay. All right, and this concludes our first day of probability.